Did everyone get this kind of diagram of numbers? How about answering those couple of questions? So you notice the best NPV was that 30 million tonnes processing capacity and 80 million tonnes of mining capacity. So interestingly, processing wasn't economic by itself. A processing expansion wasn't economic by itself, but with the mining expansion, it became economic. So that's just an indication of how all of the policies are actually related to each other. You can't just look at mining. I mean, that's actually what some people do. They just look at mining, fix that policy, then they look at processing, fix that policy, and like doesn't justify a processing expansion, doesn't justify a mining expansion. The same thing happens with extra processing technology. Sometimes people will investigate a new processing technique like leaching without changing the mine schedule. So they'll do things like they'll say, can you give me how many tons of the low-grade stuff that you send to the stockpile, and we'll try sending that to leach. And you don't get a very good value from it, so nothing happens with it. But actually, if you knew that they were going to send that for processing, you would change the mine plan and send them higher grade stuff. Maybe increase your mining rate and give them more, better quality material that they can actually make a new processing stream work. Any thoughts on opportunities to increase the value of the project? Further increase the value of the project? Stockpiling. Good option. Any other ideas? Sorry, the what?
Maybe a recovery versus capital trade-off.
Yep. Processing unit costs, yeah. If there's any cost that you can reduce, if there's any recoveries you can increase, if there's any revenues you can increase, then that will all help. I was thinking more from just this mining processing sort of options that we've been looking at.
Maybe refine your mining capacity to 75 and 85. Looks like you're sort of at a saddle point there.
Yeah.
Get it a little bit better. Looking at a 110 scenario, just because you've got a peak right on the edge of your surf craft.
Yeah. So that's what I was looking for. Yeah.
It doesn't work.
It doesn't? You checked it?
Yeah.
Oh, good. That's cool though, isn't it? To actually run the numbers and test. It's so you get a bunch of information like that, and it makes you ask questions. Oh, I wonder if we're at a saddle point. I wonder if this. I wonder if that. And then go and try it. Cool. Well done. It's another very good question. Let me answer your first question though. Just before, while we're doing this, when should these changes that we've just been doing impact your ultimate pit limits? And I think the insight that I particularly want to observe in that question is that this impacts the ultimate pit limits. Like for a lot of people, like this is one study, you do this, you set it, and then you go and look at pushbacks. You do that and set it. And actually they're all related. Now, the other thing about that particular question is that really your ultimate pit limits should be defined using NPV. Now, that's a little bit difficult unless, with the tools like when you use the Lurch-Grossman algorithm, that doesn't have the NPV. It has a cash flow type of analysis. Cash flow skin analysis that's being done. So how you figure out the best ultimate pit limit is you need to use a schedule. Now the better schedule you have, the better result, the better ultimate pit limits you'll get. So if you have a very crude schedule, if you just mine, you know how you'll often create shells, pit shells. If you just mine the first pit shell, when you get to the end of that, start mining the second pit shell, you've got no ore for a couple of years because you didn't do any stripping ahead. So if you had a really bad scheduler, then you'd get really bad estimates of where the ultimate pitch limits should be. So the better scheduler you use, you'll get better values. So we will typically take like all the shells and run them through some schedule optimization using COMET. And because within that we can have sinking rate limits, we can have, you know, if you've got 3 different processing plants, if you've got stockpiles, and you know, you can build a really good model of the cash flow and the resource consumption to figure out what the value of each of those pushbacks are. And then what we'll do is we'll typically okay, so if this is pit size, and we have NPV over here, with small pits you typically climb in net present value, and then you'll get some point after which there's no improvement in value. Now, if you plotted not NPV, but if you plotted cash flow, if you plotted cash flow, you might have something like this. So this is saying that at this point here, this is what, like some software call it a revenue factor 1. This is revenue factor 1. It's quite common that by the time you take into account that you do the waste mining several years before you get the ore from it, and therefore there's quite a bit of discounting applied to the waste that you don't have applied. The discounting applied to the waste is not very strong, whereas the discounting applied to the ore is quite strong, in which case a whole bunch of these shells which appear to be revenue generating actually become negative. So this is what you'll get. The best size pit is normally quite a bit less than that. So it's often like a revenue factor of 0.7 or 0.8 or something like that. And there's no real way to look at this graph of cash flow and say, oh, it's back here. You actually have to run schedules to figure this out. So we'll typically have all these shells, so all these different pits here, and we'll just try, should we stop after pit 1? Should we do 1 and 2, 1, 2 and 3? And we'll just keep going until we find that the best net present value was this shell here. Now you've got the next problem, is the shells are not viable to be mined by themselves because they're too thin. So then what we'll do is we'll start doing some groups of shells. So we might do a couple of groups like this, but then should we just divide it like this? Or maybe the last group should be, here rather than the bigger one. Or maybe we even have to do a tricky sort of thing where we do this shell and this shell together so that they're a reasonable size. So you start grouping shells to try to figure out where the best NPV is. And often when you group shells, because you're grouping stripping together and doing some stripping for a shell that's a little bit later, you're doing that stripping earlier because you've combined it in a bigger pushback. Often the best size NP will go down again. Getting a few too many diagrams here. So maybe it's down here. And then what you do is you'll start to make practical pushbacks out of these ones. Ones pushbacks with ramps and that obey the other more detailed design parameters to see whether you should tweak this a little bit further. You know, can it be out a little bit more or in a little bit more? What gives you the best value? Ultimately, the best value option is what you're going to pick. So even though this process isn't undertaken by one press of the button, you know, by running several different cases, you can figure out what's the best ultimate pit limits to run with. And if we change mining and processing rates, then these numbers might change as well. So you really need to go back and redo that work. So you end up finding that you want to do a whole bunch of cases and then something changes, you need to do them all again. And then something else changes and you do them all again. Because, and often you'll end up with hundreds, if not thousands of cases that you want to rerun. So that was a great question, thank you. And the second question? The one that you just asked before I answered the other one. Okay. Minimums. Okay. Minimums are a fascinating topic. Let me just try to figure out a good answer. No. Okay, so minimums, I think what you should, every time you see minimums, it should be like either a yellow or a red flag to say, be careful. Because minimums are just notoriously used for like, I want this to happen, I want this behavior to happen. The difference between minimums and maximums, like normally when you hit a maximum constraint, it's a real constraint. You hit the maximum and something overflows. You know, you don't have any more time, you don't have any, something breaks with maximum constraints. With minimums, what breaks, what overflows, what doesn't work when you hit a minimum? And maybe you can think of something, but quite often it's not a real constraint, it's an artificial constraint. And we have to be really careful with artificial constraints because they will actually drive value and destroy value. And so, as an initial comment is to be really careful of minimums. Don't put them in unless you are sure that they really are a constraint. But some more feedback on minimums is that, so that's kind of a second thing, that often minimums can be transcribed or transformed into maximums, and the maximum is the real constraint, which you really want to model anyway. And then you also have minimums quite commonly in marketing specs. So the iron ore should be between this and this, the phos should be between that and that. So you have minimum specs from the marketing requests. Or the processing plants might say, look, we really want arsenic between this and this. Or normally it's not really a constraint. It's not something that breaks. It's something that costs money. Or it's something that, like costs is one of the things that they are often trying to model. It's not that something breaks, it's that if we have too much silica in 1 year, then we need too much acid. We don't have enough acid to handle that silica, and therefore we will impose a minimum amount of silica so that we don't actually have a maximum, a too big a maximum later. So it's trying to sort of mimic a behavior. And what I would rather do is really put what the constraints are. Not put an artificial one, put the real constraint, which are normally maximums.
It's a real constraint.
Okay, so what that is not actually a constraint, it's a cost. So if you implement it as a constraint, then you'll get a different answer. So really what you're saying is, well, normally those sort of contracts, contract mining, is that you've said, it's a take or pay type contract. So either you take 10 million, you mine 10 million tons, or you still pay for it anyway. So there's no motivation for you not to mine it because it's like free. I mean, you're obliged to do it. But if you put it in as a minimum, then it could be that other factors come into play where you're making a lot of other things happen just so that you can meet that minimum. It's not actually good for value. And what should be better to do is to model that as, okay, we need to pay this much money for the contract. So any mining from 0 up to 10 million tons is free. Anything above 10 million tons, costs whatever the other rates are. And so if you model it more appropriately as a cost, then the need for a minimum disappears. So whenever you see a minimum, it's a red flag, or at least a yellow flag. It's a danger sort of thing. They can often actually be trying to mimic maximum constraints, and so it's better to actually model the real constraint rather than an artificial minimum. And then you can often change it from a constraint to a cost. And if you model it as a cost, it's normally more appropriate anyway, and it has the right effect on the schedule. There is a natural, a lot of people will say, let's have a minimum constraint on the processing plant, that you must have the processing plant at least 90% full. The reason why we fill the constraint, the mill, like all these schedules are trying to fill the mill, but they don't do it because we've got a minimum. They do it because the objective is maximising the net present value. So you naturally fill the mill so that you make more money. You don't artificially do it. So where I've seen minimums is normally in software that don't really have a net present value objective. If your objective, like if you're scheduling and you're really, you can just maximise the cash flow this year, then the reason why you strip is not because it's a good thing to do, because stripping just costs you money, you get no value this year. It's next year or the year after or several years down the track. So the reason why you do stripping is people put in a minimum amount of stripping. And really the reason why is that your objective is not maximising NPV, it's just looking at this year. So that's another sort of indicator that your objective is not NPV. And unfortunately some people will claim that it's NPV, and you have to kind of look at the fine print. Is it actually optimizing based on NPV, or is it doing some analysis and then calculating the NPV at the end? And it's not maximizing NPV, it's actually maximizing a short period of time. So we don't normally model minimums. We do have the ability to model minimums, not so much in this one, but in the other software, to try to keep grades within a certain blend. But it's something that as soon as I see someone using one, I think, do you have good reason for that? So we try not to use them, not because we don't like them, but because they're not really appropriate in many occasions. I think also sometimes those marketing contracts that say you have to keep the grades between this and this, really we should be going back to marketing and saying, like, what are you doing this for? What breaks? What happens? Oh, we can't sell it. Really? You can't sell it? Well, get another job that you can sell it. No, I wouldn't say that, but often those marketing contracts, it's easy for them to sell the same thing year after year. It's harder work for marketing to actually have something that goes up and down with the resource. This year we've got great stuff, next year we've got not so good. A couple of years later we've got great stuff again. It's harder work for marketing to sell that. But maybe that's what they need to do, is to go to their customers and say, look, this is our profile. This is what comes out kind of easily out of the resource. And now, You know, we can give you a couple of years of great stuff here, then we're going to have a few years of pain. Is that going to work for you? No? Okay, well, we can change the order of the mine plan, but it's going to cost a fair bit more, or a little bit more, or, you know, whatever it is. So getting that sort of interaction between the mining and the scheduling and the marketing and the ultimate customer is a great idea. And to sort of push back, particularly on minimums, that they're really, you know, they're often not real. Has anyone else found that? I'm sure you will, but you're just
It's
good at all this.
what we call, probably heard about value in use curves. And this is just about how you reflect what the market may think of, if you're talking iron or phos for the next 10 years. There's a penalty on it. You can produce as much as you like.
Yeah.
You just get discounted when you're trying to sell it.
Mm.
And if you just put that in a real, you simulate that curve, you're trading it off.
Yeah. Yeah, so instead of having a minimum FOS, you just have a penalty for FOS. The more FOS you have, you know, like really for the iron ore furnaces, they have to, it costs them to have FOS in there. So if they can add something, well, cover their costs. But that would be better to model it that way than just saying, oh no, we've got a maximum minimum FOS. Oh no, we can't do it this year. It's easy next year. Well, instead of completely changing your mine plan, why not go back and see where that's a real constraint? And minimums often are not.
Yeah, often you'll find that there's quite a sharp change in the slope of a cost curve or something of the sort, and these sort of limits get wired in somewhere before the curve starts. But again, if you can come back and get the real relationship, and you know, allow for the fact that we're blending and a lot of other things that may come in to enable yourself to pull yourself back below the area where the costs start to go up or the rate drops off rapidly or something of the sort like that is often the right thing to do. Model the real thing, as you say.
So you want to apply those sort of techniques to, you know, like to all your costs and all your constraints. Make sure that when someone says the processing capacity is this, you know, what actually breaks when you get more than that? Well, actually, it's the primary crusher that does this, or it's the SAG mill that does that, and so find out actually what the real constraints are, and you know that will involve going and having discussions with the metallurgist, you know, like and not just because something's wrong, you know, just go and take an interest, you know, like it's a great compliment if ever you know a geologist said to me once, "Are you a geologist?" I thought, yeah, you know, like I was so interested in geology that they thought I was a geologist, you know, and likewise with processing, you know, and marketing and finance, you know, take an interest in the topic, you know, like it's typically no one else does, you know, no one is really takes it as under their wing to be responsible for the whole business and the optimization of the whole business, and that's what we're trying to encourage. Everyone says that you know, strategic, you know, analysis is, you know, in the top 10 objectives for every CEO in the planet. You know, like it's right up there, often in the top 3. You know, it's really important. Everyone says that. But you know, a lot of the financial people don't really understand that the mining business. So you guys are in the mining business, so why not understand the financial business better? And so that you can have a discussion with them and you know, talk about costs and talk about depreciation and understand write-offs and why does that matter, and tax, and you know, like just first time I went to a processing plant, it's like dirty, smelly place. Like I didn't want to be there. You know, all the railings are all dirty and stuff like that. And like I don't know what I'm looking at. You know, it's noisy and dusty. Oh, not dusty, but you know, like. And I don't even know what I'm looking at. You know, now I can walk through a processing plant. Oh, that's a SAG mill. Yep, and it goes into the ball mill. Yeah, there's some big flotation tanks, and you know, I know what an autoclave looks like now. You know, I can say the word. I can maybe not spell it, but yeah. So you know, like, and each time you go to the processing plant, you probably learn a little bit more. And you know, you might find there's a bit of resistance when you go and talk to other disciplines. It's like who are you? Like, why are you asking about processing? Actually, the next area is about processing. And with this, the processing engineers, when you first ask them, what's the throughput recovery relationship? There's often like, you're asking me about that? You go away and do your mining stuff. I know what I'm doing, thank you very much. So, there's we need to get over that. Like they need to get over it, we need to get over it, but like to realise that we're all on the same team. If I share what I'm doing with you, maybe you realise, oh, okay, that's how it works. Well, actually, that'd be really handy. They don't have the tools for schedule optimization. All they can do is you give them a schedule, they can just play with those numbers. What if they had the ability to tailor the feed that goes into their processing plants? Well, that's really interesting, but they can't do it. Well, but you can. So, yeah, just building those relationships are key. We've talked a lot about technical information here, and technical kind of optimization and mathematics and how you do it and what this algorithm, that algorithm. But really, at the heart of all this, there's people. And people trump, without a doubt, people trump, maths and optimization cleverness. So, it might seem a bit weird coming from someone that sells mathematical cleverness, but an optimization software, but really people are more important than that. And a good person will find value that the software doesn't, the clever algorithms won't find by itself. The person, it'll be a person that'll come along and say, let's try a mining expansion. The software probably won't do it by itself. A person has to say, well, let's get the software for a start. A person has to say, what cost should we plug into this? Let's go and get some costs. How much does it cost to expand the mill? People do that. And likewise, people say, I'm not doing anything about expansions. The mill's been done. It was done in the feasibility study 15 years ago. I know the gold price is, like 3 times more than what it used to be then. But there's no need to change it. It's people that increase value, and it's people that destroy value. And so, I think we want to have a much greater focus on people, and how to treat people well is a good start for some of that, and how to realise that we as people are also amazingly valuable, just because we're people. I think that's at the core of a lot of the troubles of, you go to change a mine plan, and people don't want to change the mine plan because they lose their job 3 years earlier. And why that's a problem is that, their friends also know that you're the mine planning engineer that said the mine should shut down 3 years earlier. And they're not really happy with that. They tell your wife they're not happy with that either, and your kids are at school with their kids, and yeah, it's a big mess. And so to have the confidence in yourself that just because you're a person, that makes you special. And that makes you incredibly valuable, an innate value in people. Not a phony value, a true value in every person. This is something I think impacts how we respond to change. And so, I haven't talked much about it. I'd be happy to, but really we're talking about mathematics and technical optimization, things like that. But actually, there's a people side to this which is more important. And I touched on people in terms of the shareholders. And when you start to bring it back to people, it starts to become, I think a bit more, it'll impact the decisions a little better. I was at a workshop a few days ago with one of the guys in this class, and they talked about, have you seen those little men around Brisbane? The little is anyone who's been to Brisbane, hopefully on all the sides of the roads, you have all these little, instead of markers that, tape that says don't cross this line, they have these little yellow people. Has anyone seen those? Yeah? And have you wondered what they were? Well,
don't crash into or don't go off the road.
Yeah, don't drive over people. And everyone knows that. They're happy to drive over tape, but not over people. Okay. Yeah, fascinating. So when you sort of, I think one of the concluding comments was, if we can personalise safety, it makes safety work a lot better, and safety initiatives work a lot better. I also think that if you personalise strategic planning, it'll make strategic planning work a lot better. So anyway, a little bit of a distraction. I wasn't planning to go down that path, but there you go. Good questions. Okay, so the next area that we're going to look at is something quite different to what we normally talk about. So 8.7 is the area that I'm wanting to look at. I'm just going to try to get a diagram up on the screen for you. Well, I can't see a diagram I can just show, but I've put the diagram at the top of the page on page 8. In section 8.7. So, so what we have here is a recovery throughput relationship. Now these are actually very common, but what they're saying is that, like in this case, what we're saying is that you get the full recovery until you get to 25 million tonnes throughput through the mill. So often the recovery, it's not actually 100% recovery, it's 100% of what the block model says the recovery should be. So that's why it's 100%. It's a bit of a large number. So what happens, you'll have a block model, it'll say a particular block's got 80% recovery. And up until 25 million tonnes, you'll get that full 80%. But if you step over 25 million tonnes, you'll start losing recovery. So now there's ways that you can step over the throughput, but each one of them you sacrifice some recovery. So for example, in the lots of mills have if you've got SAG mills, if your main constraint through your processing plant is a SAG mill, semi-autogenous grinding mill, then what happens is you've got this plant rotating with some steel balls in it and things like that. You throw your rock in the start, and then what comes out is crushed rock. But when it comes out, not everything is crushed as fine as you would like it to be, and so they have this grate at the end, a sieve at the end of it. Everything that's fine just goes straight down through the sieve and continues to be processed. Everything that's too coarse gets fed back around and goes through the mill again. So what happens is, if you increase the size of the sieve at the end of the SAG mill, then more stuff will go through. You have got less recycling, and therefore you can fit more material into the SAG mill, in which case your throughput rate will increase, but the rock coming out of it is a little bit more coarse. What happens is, when you get coarse rock, it doesn't recover so well through the flotation stages, things like that. They start sinking instead of floating and things like that. So you can trade off some throughput, so get some more throughput, but you lose some recovery. Some other examples of this are in the flotation circuits. The longer you leave material float, the better recovery you'll normally get. So you can trade off the time that that material stays floating for the recovery that you get. But the time means that you've got less material you can put through. Another example is in the leaching. So in leaching, if you put material onto a leach pad and leave it there for 30 days, you get one recovery. If you leave it there for 60 days, you get a little bit more recovery. 90 days, a bit more. And people will figure out how much recovery they want, and they might set it, okay, it's going to be 45 days, and with that we get 70% recovery. But if you left it for 60 days, then maybe you get 80% recovery. And if you left it for only 30 days, maybe you'd get, I don't know, 65% recovery or something. But you've got different throughput recovery relationships. It's actually all through the processing world, they have these relationships. And generally as mining engineers, we don't know anything about them. That's why when I was saying the processing people, you'll say, oh, what's the processing capacity? And they'll give you this big long spiel, but we just care about the 25. It's 25 million tonnes a year. But actually it's 25 at this condition, that condition, that condition. But if you really want to push it, you can get 35 or 40. So that's what this relationship's about, is that if you push the more material through the processing plant, you'll sacrifice some recovery. And the reason why you'd want to do that, you sort of might think, oh, sacrificing recovery doesn't sound very good. We're trying to maximize recovery. No, not exactly. You're trying to maximize the value, both in this year and the following years. And quite often, if you send more material through the processing plant, even though you drop recovery, you'll actually make more metal out at the end of the day, the end of the year, in which case you'll make more revenue. The problem is you've just consumed more resource, so you'll typically only want to do that at the beginning of the mine life, whereas at the end of the mine life you'll often not want to do that. So it's a little bit like cut-off grade. It's a policy that you can change over time. So that's what this next exercise is about. And it's kind of a complicated thing to do in practice. And so what I've done in COMET ONE is I've just given us 3 examples that we can pick from: a high, medium and low throughput recovery relationship. So if we pick one of those, I think we're going to pick the high one. So we don't need our input parameters at the moment. What the high one says is that we can have 100% of the throughput and 100% recovery, or if we go higher, we can get 110% throughput, but we lose 2% recovery, or we can go even higher and we can get 120% throughput and we get 96% recovery. So you can go higher throughput, but you end up losing recovery. The low one means that you can go to lower throughputs, but you end up getting more recovery. And the medium is something between the two. So if we just have a look at the high throughput recovery relationship. Has anyone come across these relationships in the field? Yeah? What sort of relationship have you come across?
We do a lot of mine-to-mill work, so
Okay.
based on that, we're essentially looking at increasing blasting intensity if it's needed.
Yep.
So that's where we generally see you send through finer material, you're increasing throughput in the mill,
Yep.
but your recoveries might be slightly lower,
Okay.
and sort of look at the trade-off and then look at...
So you have some sieves that you determine how much fine material you send through?
Yeah.
Yeah, cool, yeah. And Peter, what?
Zambia operation, the
Same thing, yeah. One of the really interesting things about this is that, this particular case you see it's another 5.5% more valuable. Like, this is a big number. Like, 5.5% of the NPV 1% is a massive number. All the cost reduction programs that people do and things like that, if they could get 1% of the net present value, that would be massive. Often you're just looking at, 1% of the costs. 1% of the net present value is a huge number. So, and this is like $450 million. I mean, that's a big number too. But one of the really good things about this is that it doesn't normally cost you much money. So like to replace a sieve, like if you've got one, a screen size, you have to replace them anyway. They wear out over time. Well, the next time you get one, you just get a coarser one, or you get a finer one. Or, you have to replace them anyway. It costs you virtually nothing. And yet you get to increase the throughput quite a bit and increase the value quite a bit. So a lot of these things actually do cost you in terms of mining capacity. You need to be able to speed up the mine. But even if you can't speed up the mine and you just send material to process instead of to the stockpile or the waste dump or to the leach or something like that, there's still a lot of value here. So let's have a look at this and see how we got that extra value. So we are able to go up to, in this example, 120% of the processing rate. So if we got 25 million tonnes a year processing rate, so 10% of that would be 2.5, so it's another 5. So we could go up to 30 million tonnes processing. And yes, we take a hit on recovery, but that's what it is. So this first case, our base case, 25 million tonnes pretty much every year. This next one, we've gone up to 28 here, down 27. Bit hard to read the difference between those. We have gone up to 30 for a few years, back down to 28, 29, a few years at 30. So what you notice is that it doesn't just use the maximum capacity just because it's there. Just because you have it doesn't mean it uses it. It's using economics to drive all these decisions. It's a bit like what we saw with the mining capacity. Even though we had plenty of mining capacity, it doesn't always use it if economically it thinks that's a bad thing to do. But one of the things you can note about this I was going to say, generally it's higher at the start of the schedule. But because we're hitting this mining capacity so much, that's actually pulled it down a bit at the start of the schedule. You notice the cut-off grades have changed, quite a bit. We generally have cut-off grades around, like say, maybe they average 5, whereas up there maybe they're averaging 6 or so. In fact, we can look at what the actual numbers are. The cut-off grade was 4.7 and 6. So in order to fill the mill with more material, we have found that extra material just by dropping the cut-off grade. Well, sometimes just dropping the cut-off grade. You probably notice on average we're actually mining more material as well, mining rock a little bit quicker. We're sticking at that 70 for many more periods than we were up here. So it dropped down to 66 quite a bit. You can have a look at the impact on the cash flows, the costs, the revenues, the profits. You notice that we finished the mine a little bit earlier. So you think, well, if I can process it more quickly, then we'll probably finish the mine a little bit more earlier, which is what happened. Well, I think we'll... Any questions on that?
Where are the inputs for that?
Yeah, how are you setting it up?
I just set that up based on this comparison case here. I did a comparison case that allowed a variable throughput recovery. So it's not something that you can manually do. It's something that there's an automatic example of it to give people an idea whether there's value in that. What I'd like to do is just show you how to get your own data into this. So section 9.2, we talk about that. Okay, so in section 9.2, I'll just show you how you can do that. The rock properties here are all, you can change your number of attributes and things like that. So there's a bunch of options you have here. So if I want not 4 but I want 5 attributes, then you can change this. It rebuilds the data that's sitting below here. It just sort of recalculates things, although it's nothing really to recalculate. Oops. So you set up these parameters as to how many cut-off grades you want, how many increments you want, how many attributes you want, and then this information here, you can select all of this, select all, copy it, go into Excel, paste it. Here's my new attribute over the side here. So if I wanted a new recovery or something like that, I could put the new recovery in there. So you can just edit this back in Excel, come here, paste it back in here, and say update. So you should be able to get your own reserves into this relatively easily. What I'd suggest, I have in section 10, like a path forward that you can take. If this is something that you think, look, I actually think there's a fair bit of value in this, I'd like to pursue it, you can use this as a way to get the size of the prize of doing an optimization study on your project. So what I suggest you do is obviously in 10.2.2 there's different costs that you want and productivities. Sorry, 10.2.1 is getting the resource model. So rather than getting a sequence of mining for your project, I would just get the grade tonnage curve for your whole project. So look at what's inside your ultimate pit shells, get the grade tonnage information for that. That's actually a great way to start. You know, it's surprising how good those numbers are compared to when you do the full study. So we normally do take this another few steps, but actually just getting the grade tonnage curve for your project, update all your costs, your revenues, your constraints, your capacities, put your numbers in there, and just run some of these cases, some of these scenarios.
So if you've got a recent optimization and you've got the different shells, can you use them as your benches? And
Probably what I'd do is just get the shell that you think is your ultimate pit shell. So not revenue factor 1, maybe back 0.7 or something like that. Take that shell and everything in it and get a grade tonnage distribution for that. And then put that in to here. Just say you've got 1 increment, not 10. Put in your names of your variables. You can have more than, I've got like 4 here, but you can have more than that. And put your data in and give it a go. Thank you. All good.